for another exciting video. This time we're going to talk about formula weights and the mole. And this stuff, it's going to come back to you, and I think it's going to be pretty easy. There's a couple of tricks here, but nothing too bad. So formula weight first. Formula weight, molecular weight are the two terms that are sometimes used for this. Formula weight is basically just the sum of the atomic weights, in other words, the atomic masses. I don't know why weight is used there, because we make a big deal earlier in science about distinguishing between mass and weight, and then the terms get used interchangeably in chemistry. So, sorry about that. When we say weight, typically we mean mass. So it's the sum of the atomic masses for the atoms in a chemical formula. Okay? So if we want to know the formula weight of calcium chloride, all we do is we add up 1 calcium, which if you look on the periodic table at the atomic mass, which is the decimal number, then you're going to see calcium is 40.1 approximately AMU. Chlorine is approximately 35.5 AMU. That's rounding a little bit, but it's close. And notice here that we multiply the chlorine by 2, and the reason that we do that is because there's 2 chlorines in the compound. So the ratio there is 1 calcium to 2 chlorines. So when we add up those atomic masses, we end up with 111.1. Okay? So again, pretty straightforward. And formula weight is the term that's usually used for ionic compound, although a lot of times it's used interchangeably. So, but formula weight technically is what you'd use for an ionic compound. For a molecule, you'd use molecular weight, okay, MW. So molecular, I don't know why I said MW or why it's like that on there. I've never heard it called MW before, but anyway. That's the sum of the atomic weights of the atoms in a molecule, just like formula weight, but usually this is for covalent compounds instead. Again, these terms are used pretty much interchangeably. It's not that big a deal which one you use, as long as you recognize that both of them basically mean the same thing. So for a molecule of ethane, C2H6, if you add those up, carbon's about 12 on the periodic table. There's 2 of them, so we multiply that by 2. Hydrogen is about 1, and there's 6 of those, so we multiply by 6 and just add them together. Really simple stuff. Okay, percent composition. Oh, sorry. We've got a sample problem here, so let me get a notebook thing open. This is why these videos take so long, is because I don't have this stuff ready ahead of time. So I'm going to sit here and wait for Smart Notebook to open for just a minute. I almost said Smart Notebook. Smart Notebook, more like Smart Notebook. Anyway, I'm just killing time because this is taking a really long time to open. I could have just paused the video. I'm sorry, I'm wasting your time. Okay, here we go. So right now we are looking at the sample problem on the first page. It says calculate the formula weight of sucrose and calcium nitrate. Okay. Again, I don't think we need to go into a lot of detail on these. I think you guys are fine here. Carbon is about 12. Okay, I'm going to round a little bit here, 12.0 AMU. And we have 12 of those. And then we're going to add that to the hydrogen here, which is about 1.0. And there's 22 of those. And we're going to add that to the oxygen, which is about 16.0. And there are 11 of those. Okay. When we multiply and add all those together, we're going to end up with a fairly big number here. I'm getting 342. And we're going to report that as AMU because that's what we've shown in the example so far. Now what we're going to talk about in a minute, AMU and grams per mole are actually interchangeable units. Because on the periodic table they end up being the same number. When I say they're interchangeable units, they don't necessarily mean the same thing, but they're always going to be the same number when you're looking on the periodic table. Okay, and then B here, calcium nitrate. So calcium is 40.1. We already saw that in the example. And didn't need to do that because there's only one of those. You don't have to do that one part. Now you have to be a little bit careful here, but I think you guys are going to catch this. There's 2 nitrogens there because it's in parentheses, so we have to take 14 times 2 and add that to 6 oxygens, which is 16 times 6. Okay, and we do all that. Again, it's just easy math here. I'm getting 164.1 AMU. Okay, very simple stuff. So that's that. Align my board. Let's talk about percent composition now. Okay, percent composition comes from the idea of formula weights. Once you know the mass of the entire compound, then you can compare the parts of that compound and figure out what the percentage by mass is for each of the different elements. Okay, so this is just a basic percentage problem. Percentage of the element equals the number of atoms times the atomic weight divided by the formula weight of the compound. Okay, and then times 100. So percent of carbon and ethane, because we have C2H6. Then your percent of carbon there is going to be 2 times 12, because there's 2 carbon atoms in that particular molecule, and they're each 12.0 AMU. So we multiply those together and then divide by the total atomic mass of the entire molecule. Okay, and so we end up with 26 divided by 30. I'm sorry, 24 divided by 30. Can't do math. Times 100, that's going to give us 80%. Okay. And we have a sample problem on that one too. Calculate the percent composition of sucrose. So sucrose, again, is C12H22O11. And when it says calculate the percent composition of sucrose, it means calculate the percent composition of every element in sucrose. Strange. So we know what the overall is. I just got rid of that. I wish I hadn't. Okay, the overall for sucrose is 342 AMU. Okay? So 342 AMU. Got to keep that number in mind for our total. And C12H22O11. I'm just going to write this up here. Okay. So we've got 12.0 AMU times 12, because there's 12 carbon atoms, divided by the 342. That's going to give us the percent of carbon. Okay? Well, times 100. It's going to give us the percent of carbon. Okay? So when we do that, 144 divided by 342, about 42.1%. Okay? And if we want to know the hydrogen percentage, save a little bit of time here. Hydrogen is 1.0 times the 22.0 divided by 342 times 100 equals the percentage of hydrogen, which is going to be equal to 6.4%. I don't know what's going on with my smartboard right now. This is very strange. Okay. And then the last one here, oxygen, 16.0 times 11 divided by 342 times 100. And that's going to give us the percent of oxygen in the compound. And that's going to be about 51.5%. Okay, and then you'd probably want to check and make sure these add up to about 100%. 42.1 plus 6.4, that's going to give us 48.5. Is that right? 48.5. plus 51.5, that's going to add up to 100, okay? So that's that. Again, pretty simple stuff. Alright, so let's talk about the mole now. Moles. Hopefully you remember Avogadro's number, and you remember, well, if you don't, you're just going to have to re-memorize that one, okay? Avogadro's number right here, 6.02 times 10 to the 23rd. I think it's technically 6.022 times 10 to the 23rd. Well, actually, it keeps going further than that, but it depends on the book how it will be reported. 6.02 times 10 to the 23rd, I think, is probably good enough for the AP exam. I'll be giving you an equation sheet soon that will help you out as far as knowing what numbers to use for your constants and everything like that. So I think that one's on there. You might not even have to memorize it. 1 mole of carbon-12 has a mass of 12 grams, so that's kind of where that number comes from. And basically, when you're doing a conversion here, you're just doing dimensional analysis, okay? So this first problem here, it says, without using a calculator, arrange the following samples in order of increasing number carbon atoms. Let me get back to my... smart notebook here. Okay, so 12 grams of carbon-12, 1 mole of C2H2, or 9 times 10 to the 23rd molecules of CO2. Alright, so without using a calculator, we want to try and figure out if we can know how many atoms are in each of these things. Okay, and okay, so I had to think about that one for a second. I didn't want to waste your time like I tend to do on these, so I paused it and thought about it. So we've got 12 grams of carbon-12, okay? That is the same thing as 1 mole, because we just said that's the definition of a moles. Carbon-12 has a mass of 12 grams if you have 1 mole of it, okay? So that's 1 mole of carbon, okay? Now this next one, 1 mole of C2H2, that's actually 2 moles of carbon atoms, okay? And hopefully that makes sense to you. If you have 1 mole of the entire molecule, there's 2 moles of carbon in that 1 mole of that entire molecule, because each molecule contains 2 carbon atoms, okay? If that's not making sense, if I'm going to set this up, I've got 1 mole of C2H2, and if I do dimensional analysis here, my moles of C2H2 go on the bottom, atoms of carbon go on the top. So there are 2 atoms of carbon for every 1 mole of C2H2. I'm sorry, that's not right. 2 moles of carbon. That's ridiculous. 2 moles of carbon for every 1 mole of C2H2. Okay, there's a lot more atoms than that in a mole. But that's how you set up that ratio, okay? And the reason for that is the formula there, the C2H2 formula, it actually tells you that there are 2 moles of carbon and 2 moles of hydrogen in each mole of C2H2, okay? And then this last one here, 9 times 10 to the 23rd molecules. Well, that's more than a mole, okay, because 1 mole would be 6.02 times 10 to the 23rd molecules. But it's less than 2 moles, because 2 moles would be 12 times 10 to the 23rd, okay? So it's actually going to be right in between here. I don't know, somewhere around 1.5 moles of carbon, okay? So, to arrange these in order of increasing number of carbon atoms, the 12 grams of carbon-12 would go first. And then we would have the 9 times 10 to the 23rd molecules. And then after that, we would have the 1 mole of C2H2, okay? And hopefully that makes sense. Alright, next sample problem, calculate the number of H atoms in 0.35 moles of C6H12O6. Okay, I want to make sure you guys get this, because this is a problem that they might throw at you at some point, and there's a little bit of a twist to it that you got to watch out for. Okay, so we've got 0.35 moles of C6H12O6 glucose. and we're trying to figure out how many hydrogen atoms there are, okay? So moles is going to go on the bottom, C6H12O6, and there are a couple ways you can do this. I'm going to go to molecules of C6H12O6, okay? In 1 mole, there are 6.02 times 10 to the 23rd molecules of C6H12O6. And then we have to set up another conversion because we don't want molecules of C6H12O6. We want atoms of hydrogen. So I'm going to, in every 1 molecule of C6H12O6, there are 12 hydrogen atoms. Okay? So that's going to get us to the number of hydrogen atoms. 0.35 times Avogadro's number times 12. And what you end up getting there when you do this, you're going to get 2.5, let's do sig figs here, 2.5 times 10 to the 24th atoms of hydrogen. Okay? That's how that works. Alright, next we need to talk about molar mass. So, get back to the PowerPoint here. Okay, we already talked about all that stuff. So by definition, that's the mass of 1 mole of substance, okay? Grams per mole. We talked about this a lot last year. This comes from the periodic table, okay? Molar mass of an element is the mass number. Ooh, I don't like that. Sorry. What I mean there is it's the atomic mass, not mass number. Remember, mass number is just the protons plus the neutrons. Okay, so change that to atomic mass. Sorry about that. And the formula weight is going to be the same number as the molar mass. Okay, they're actually different things. The AMUs is talking about, that's a very small unit used to measure things that have masses like protons and neutrons. And the molar mass is actually talking about how many grams do we have in 1 mole. But it works out that they are the same number on the periodic table. Okay, and they're that decimal number on the periodic table. So, oh, we got a sample problem there too. We want to know the mass of the mass of 1 mole of glucose. Okay, so we've got 1.000 moles of glucose, which is C6H12O6. Okay. And you can go straight from moles to grams. You just want to know how many grams are in a mole, and you're going to find that out from the periodic table. Okay, and the way we do that is we find the formula weight of the glucose, and that's going to tell us grams per mole as well as AMU. Okay. Gosh, seriously, every time I pick this up. Okay, so when you figure that out, C6H, I don't remember if we did that one or not, but basically you're going to take 12 times 6 because carbon's about 12, plus 12 because hydrogen's about 1 and there's 12 of them, plus 6 times 16, so 180 grams in 1 mole of glucose. You might remember that from last year. We used glucose every once in a while. So this is an example of the kind of problem they might put on a multiple choice section, because as you can see, we've got 1 mole of C6H12O6, and it's not that hard to multiply 180 by 1. So 180.0 is our grams per mole here. Okay, and that's going to be your unit when you're finding molar mass. And actually there, I was just finding the mass. I'm sorry, that's just going to be grams for your unit. If they're asking for molar mass, it'd be grams per mole. So just pay attention to what they're asking you for. Okay, moles also give us a bridge. They help us to get from one thing to another. So From moles, we can get to the mass of something. From moles, we can also get to formula units or atoms. Formula units is the general name for things like atoms, molecules, ions, that sort of thing. Those are all encompassed in formula units, okay? So moles allow us to get from one place to another, okay? And a lot of times what we'll do is go from grams to mole or from moles to grams, but you can figure out, if you know how many grams you have, you can figure out how many atoms of something there are going through moles, okay? This gives some relationships here. So you've got, for example, atomic nitrogen, which has a formula just N, has a formula weight of 14.0 AMU, okay? And notice it also has the same molar mass, 14.0 grams per mole, okay? And there are 6.02 times 10 to the 23rd nitrogen atoms there, okay? So you can look down this chart, you can see what's there. It's fairly straightforward, okay? Now we need to talk about a couple sample problems here. You've seen this. The number of moles of glucose in 5.380 grams. Let me get back over here. Okay, so we've got 5.380 of C6H12O6, okay? And we want to figure out how many moles of glucose we have. So this is pretty easy. We're just going from grams to moles. And in 1 mole, we already figured out this is 180.0 grams, okay? And so then we're just going to take the 5.380 divided by 180. It's going to give us 0.0298888, a bunch of numbers there. We need to round to 4 sig figs, so 0.02989 moles of C6H12O6. Okay, that kind of makes sense. 5.380 grams is not a lot, so that's going to be less than a mole because it takes 180 grams to make 1 mole of the C6H12O6. Okay, mass in grams of 0.433 moles of calcium nitrate. So now we've got, you got to remember what calcium nitrate is. Calcium nitrate is CaNO3(2). Okay. Go from grams to moles here, and we're going to have to look at the formula weight of CaNO3(2), which I feel like we did that earlier in the notes, but I'm not going to take the time to check right now. I'm just going to multiply it all out, and we're getting 164.1. Yeah, that sounds really familiar. 164.1 is your molar mass there. So you take the 0.433 divided by that number, the mass, and you get a very small number here. This is going to be 2.64 times 10 to the negative third moles of calcium nitrate. And again, if you get the formula wrong here, you're going to get everything else wrong. I don't know why I boxed that one when I circled the other. Okay, last page here. How many glucose molecules are in 5.23 grams? Okay, now we're adding an extra step here, which is bad because I was running out of room when we just had those steps. Actually, I'm going to get a full screen here. Every time I miss that extend page thing, it makes a dot. And then every time I put the eraser down, it switches my page. Okay, so 5.23 grams of C6H12O6. Okay, and we want to know how many glucose molecules. Well, we can't go straight from grams to molecules, but we can go from grams to moles, and then we can go from moles to molecules. Okay? In 1 mole, there are 180 grams of C6H12O6. And in 1 mole, there are 6.02 times 10 to the 23rd molecules. Okay? So that's going to give us our answer on that one. 5.23 divided by 180 times 6.02 times 10 to the 23rd gives me 1.75. 1.75 times 10 to the 22nd. Molecules. Okay? Now, let's say that we take this one step further here, and instead of just wanting to know the number of glucose molecules we have, we want to know how many carbon atoms there are in that many grams. Okay? Now, the good news is here, we just found the number of molecules. We can go straight from the number of molecules to the number of carbon atoms, so this doesn't require a lot of extra steps here. We've got 1.75 times 10 to the 22nd molecules of C6H12O6. And we're going to go from molecules to carbon atoms. Okay? So in 1 molecule of glucose, there are 6 carbon atoms. So all we have to do is take our answer and multiply by 6. And when we do that, we should get 1.05 times 10 to the 23rd carbon atoms. Okay? Hopefully this is all coming back to you now with the dimensional analysis, remembering how to do all this. Again, I don't think you're probably going to have too much trouble with that. We'll do some extra practice in class. And after this, we get to start stoichiometry, which is going to be fun. Alright, see you next time.